What specific challenge in scaling existing graph transformers does your method aim to address, and how does this relate to the memory and time complexity of the Spexphormer model?
The specific challenge in scaling existing graph transformers that our method aims to address is the high memory and time complexity associated with training on medium to large-scale graphs, particularly with the Spexphormer model. Spexphormer has a complexity of O(nd squared plus n squared d), which becomes prohibitive for densely connected graphs with theta n squared edges, as it utilizes all original edges without asymptotic improvement. Our approach introduces a two-phase training process where a smaller network is first trained to estimate attention scores, allowing for the sparsification of the graph. This reduces the complexity to O(md plus nd squared, where m is the number of interaction edges in the sparse attention mechanism, significantly alleviating memory consumption and enabling the model to scale effectively to larger datasets. By focusing on identifying low-impact edges, we enhance the efficiency of the Spexphormer model while maintaining competitive accuracy.
Can you explain step by step how your proposed method of using a smaller network to estimate attention scores contributes to the training of the larger model, including details on the sparsification process?
Our proposed method involves a two-phase training process that begins with training a smaller network, referred to as the attention score estimator network, which is designed to estimate attention scores for a larger model. In the first phase, this smaller network, typically with a width of 4 or 8 and a single attention head, learns to identify the most significant neighbors for each node by estimating pairwise attention scores. Once trained, the attention scores from this smaller network are utilized to construct sparse interaction graphs for each layer of the larger model, effectively reducing the number of edges while maintaining important connections. This sparsification process involves selecting a fixed number of edges per attention layer based on the learned attention scores, which reduces the complexity of each layer to O(nd squared plus ndc, where c is the number of edges retained. By filtering out low-impact edges, we enhance the scalability of the larger model, allowing it to train more efficiently on larger datasets while still approximating the performance of a full transformer model.
Could you provide a concrete example illustrating the process of how the smaller network identifies important neighbors for a given node and how this affects the attention scores in the larger network?
In our proposed method, the smaller network, referred to as the attention score estimator network, is trained to identify important neighbors for each node by estimating attention scores based on the node's connections. For instance, if we consider a node I in a graph, the smaller network evaluates its neighbors and assigns attention scores to them, indicating their significance in contributing to node I's representation. After training, these attention scores are used to construct a sparse interaction graph for the larger network, where only the most significant edges, neighbors, are retained based on the learned scores. This process allows the larger network to focus on a reduced set of edges, improving efficiency and memory usage while maintaining competitive accuracy. Consequently, the attention scores in the larger network reflect the importance of these selected neighbors, leading to a more effective representation of node I, while reducing computational complexity.
What are the quantifiable improvements in performance or efficiency achieved by your proposed approach compared to existing graph transformer models as shown in your experiments?
Our proposed approach demonstrates significant quantifiable improvements in both performance and efficiency compared to existing graph transformer models. Specifically, we achieve a reduction in memory consumption by training a smaller attention score estimator network, which allows us to scale the Spexphormer model to larger datasets while maintaining competitive accuracy. In our experiments on medium-sized graphs, we show that the two memory-efficient networks can effectively estimate the original network's performance, enabling us to handle larger graph datasets like OGBN proteins, Amazon 2M, and POCIC with superior results despite limited memory constraints. Additionally, our method allows for a reduction in the complexity of Spexphormer from OMD squared plus ND squared to OMD plus ND squared, which enhances training efficiency. The experimental results indicate that our model outperforms several baseline models, including GCN, GraphSage, and Spexphormer, across various datasets, confirming the effectiveness of our approach in improving both performance and efficiency.
How did you validate the effectiveness of your method in experimental settings, particularly regarding the datasets and metrics used to measure performance?
To validate the effectiveness of our method, we conducted experiments on 12 medium-sized graphs, which included 6 homophilic datasets: CS, Physics, Photo, Computer, WikiCS, and OGBN Archive, and 6 heterophilic datasets: Minesweeper, Talokers, Roman Empire, Amazon Ratings, Questions, and Actor. We utilized a random train validation test split for most datasets, ensuring a consistent evaluation framework. Performance metrics were derived from comparing our model's results against various baseline models, including GCN, GraphSage, and Spexphormer, among others. Additionally, we assessed the maximum required memory of our attention score estimator and final networks against the original Spexphormer model to demonstrate memory efficiency. Our results indicated that the two memory-efficient networks could effectively estimate the original network's performance, allowing us to scale the Spexphormer to larger graph datasets while maintaining competitive accuracy.
What limitations have you identified in your method, especially in terms of scalability or accuracy when applied to different types of graphs, and how might these inform future research directions?
The primary limitation identified in our method is its memory intensity during the training phase, particularly for medium to large-scale graphs, which can hinder scalability. While our approach effectively reduces complexity through sparsification and batching, densely connected input graphs with theta n squared edges do not benefit from asymptotic improvements, as the original edges are still utilized. Additionally, the accuracy of the attention score estimator network may vary depending on the graph's structure, as it is not optimized for edge features, which can lead to suboptimal performance in certain datasets. Future research could focus on enhancing the estimator's accuracy by incorporating edge attributes and exploring more sophisticated sampling techniques to better capture important connections in diverse graph types. Furthermore, investigating the trade-offs between model complexity and performance across various graph structures could provide insights for developing more robust and scalable graph transformer architectures.